Welcome to week 12. So this week we're going to talk about advanced machine learning techniques and actually spend a little bit of time working with neural networks, deep learning models. Now this is a subject which in a week or in a 15-week class we could only briefly touch on. So it's not designed to be holistic, and you're not going to walk out of the course knowing everything about neural networks, deep learning models. It's going to simply give you a taste and show you how you do this within Python and give you the opportunity to experiment with this as well. So the three different types we're going to talk about is a convolutional neural network, a recurrent neural network, and a generative adversarial network, otherwise known as CNNs, RNNs, and GANs. So the assignment that you're going to have for this week is to create a Jupyter Notebook solution and implement your own advanced model. Understanding that the first iteration is not going to be the most optimized solution, or I would not anticipate that the first iteration you come up with is going to be the most optimized solution. And you're going to see that here in my demonstration that I'll show you. Going to look for correctness and functionality of the program. Make sure that you're using the right control structures and functions, the readability and organization. And again, please submit your own work. So let's talk a little bit about deep learning neural networks. If you have not been exposed to this, I'm going to show you just a couple of diagrams, walk through them, but I'm also giving you the source material so you can go back and read the more in-depth article on how these operate. And I think it's going to be good for you to review these two as well, so it's part of your required reading for this week. But as a general rule, you'll have an input layer, an output layer, and then hidden layers in between. These are called neurons, and the connections between the neurons, depending on these parameters, will have different weightings and what's also known as activation functions. So when a neuron fires, when a neuron doesn't fire, and also kind of the weight as it comes from this node to this node to this node to this node, the weight and the tuning. That's all part of the process of how a neural network works. So you may have been exposed to these in other coursework so far, but this kind of shows you just the high level of what one looks like. And then if we're going to talk specifically about convolutional neural networks, for instance, and actually this is CNN, not RNN. Let me correct that right now. Okay. Convolutional neural networks. This is a good example for this is used to identify images, for instance. So let's say this is your image. You'll take a piece of that image, and then you're going to run that through these hidden layers. And as you're kind of doing that, you're making a further selection on this. And then here's a second one, and you're looking at different features within that particular selection. So they call these convolutions, and they call these poolings. So as you get to the end of it, you're going to have a final layer, and it's going to classify it into one of four potential units on the back end of it. Again, here's a more deeper dive into convolutional neural networks. Recurrent neural networks have a feedback loop built into them. The most common kind is you're going to see is going to be the RNN and the LSTM, the long short-term memory one. So these, again, as you kind of see here, this is a better example here, how it has an input, but it also has a feedback loop of it. So think of it as going through this process of going from left to right, but it automatically comes back and it tunes a layer, and then it reruns it, and then it tunes a layer, and then it reruns it, and then it tunes a layer, and it reruns it. So it's constantly changing these hyperparameters based off of the feedback that it gets. So we see a lot of types of applications for LSTMs out there for things where maybe the first run you see that there's a certain amount of residuals that come out of it. You then want to turn around and reprocess those. This is the type of model that you would use for that. And then finally, generative adversarial networks. This is a good one that I found on Google that shows you an example of how those work. So let's say you have real images and some random input that's put into a generator, creates a sample, and then a discriminator will come out the back end of it, and then comparing the real image compared to the generated image to give you a discriminator loss and a generator loss. So the example we're going to use here is using the handwritten number data set of about 50, 60,000 different images that are out there to try to make a predictive model using a GAN. And so you'll kind of see that here in just a moment in the demonstration. So that's the three types of models which we'll talk about as part of this. I go into a little bit more detail about individual models in their sections, so read through that. But talking first about the CNN, we're going to take the CFAR 10 data set, and we can replace that with basically any data set that you want to for image classifications. But for this particular example here, I'm going to use it to classify images using the CFAR 10 data set. Load and prepare the data set, dividing it into training and testing sets. I'm going to do a normalization on the pixel values of the images between 0 and 1. Define the architecture using the sequential API from Keras, consisting of the convolutional layers, the pooling layers, and the fully connected layers that we discussed above. I'll compile the model with an optimizer, a loss function, and evaluation metrics. I'll train the model on the training data for a specific number of epochs. Think of those as iterations through the model. And then I'll evaluate the model based on a test set to obtain the test accuracy and loss, and then print those out. So here's the import statements right here. I'm going to take the basic TensorFlow. I'm going to take Keras, and I'm going to take layers from TensorFlow. I'm going to prepare the data set. This is loading the data set right here, and I'm going to load it into the X train and Y train as we've done before. To do the normalization, I'm going to divide the the pixel value by 255, obviously, to get either a 0 and a 1. And then here's the actual architecture where I'm setting up the model itself. So here's where I'm setting up different layers, different poolings that we discussed above. Then I'm going to turn around and run a flatten, and I'm going to run a dense layers on the back end of it. The activation function here is very common. It's the ReLU function that I'm going to use. And so this is a basic call to a Keras model to define the architecture. I'm then going to compile the model, and I'm going to use the optimizer, the Atom optimizer here. Again, this is a very common way to generate your model. I'm going to then print the model summary, and then to actually train the model, as we've done in previous weeks on regressions and stuff, we're going to use the fit command in order to actually train the model. I'm going to feed it my training data sets here. I'm going to go through 10 epochs, and I'm going to make the batch size 128, and I'm going to have verbose too as well. I'm going to then turn around and do a test loss and a test accuracy using the evaluate off of the model that we fit, and then print off the test accuracy and the test loss. Now, when I run this, it ran for quite a bit of time. I would say probably about 5 minutes. And here's the individual epochs. As you see, it goes through each iteration. It gives you a loss and an accuracy off of each iteration. So you can kind of watch the model as it's tuning itself as it goes over time. You can watch that as the output comes out here. And then the end of it, you see the test accuracy and the test loss pieces of it here. So this is a model that could still benefit from some additional tuning, but for a first pass, it's not bad. Second one is the recurrent neural network, and so it's going to have a very similar one. We're going to do sentiment analysis on a data set of movie reviews. So we're going to train the model on a subset of the data to evaluate its performance on the remaining data. So I'm going to load the IMDb movie review database, and I'm going to look for the number of words based on frequencies. So we also have the natural language week that we have as part of the course. This is an interesting data set. It may be something to keep in mind if you're looking at different kinds of word frequencies or doing text analytics. It's something that you may want to use in a project separately. Pad the sequences of the reviews to ensure a consistent length using the pad sequences command. I'm going to build the RNN using a sequential model, and I'm going to include the different layers that we talked about. I'm going to compile it with an optimizer, a loss, and evaluation metrics, and I'm going to train the model on the training data with a validation split to monitor the performance during training. Evaluate that trained model, and then I'm going to print the test results. So we've got very similar setup here. We're going to add the additional one, TensorFlow, Keras datasets, IMDb to pick up the actual data. And there's also a pad sequences that we want to pick up as well. So there again, if you have various length strings, you want to go ahead and make sure that they're all the same. That's what pad sequences is going to do. So the maximum number of words to keep based on a word frequency, I want to keep it to 10,000. The max length I want to have is 200 with a batch size of 32, and I'm going to run 5 epochs, or you think of that as iterations on it. I'm going to do the load data on the IMDb database in order to load it, and I'm going to set the number of words to that max features, the 10,000 number that I set up there. I'm going to run the pad sequences command as discussed. And very similar to the model build we just did a minute ago, you build the model in a similar type way, but this we're going to choose as a simple RNN. And I'm only going to have one dense layer. Now the activation sequence, instead of ReLU, I'm going to use a sigmoid. So we could go into a little bit more detail of the different types of activation sequences, but a sigmoid and a ReLU are the two most common ones that you'll see in these types of models. I'm going to then use the model compile, similar to what we've done up before, and I'm going to use this particular loss function here, the binary cross entropy loss function. That is something that's very, very common when building these types of models. So the types of settings which I'm choosing here for this model, these are all things that a base first run if you're creating a CNN or an RNN, a neural net. These are all kind of the basic settings that you would use in that case. When we talk about the accuracy and we want to try to improve the accuracy, that's where you go back and you start trying to tweak some of these different settings, such as you'd add additional epochs to it. You'll change the training time that it works on. You'll change the activation function to see if you get a different kind of activation function. And then you'll compare the results that come off of it. So continuing on this model build, we'll go ahead and run the summary. We'll go ahead and run the fit, just as we did, calling out the number of epochs and the validation split. We'll then evaluate the model based off of the criteria and then print out the test results. This again ran fairly straightforward. Within about 5-minute time it runs, and you can kind of see each epoch as it's running it, giving you the accuracy measurements along the way. Now this particular one actually came out a little bit better than the previous model, but we're going to use two different data sets obviously, so you wouldn't be comparing the two together. Now this one's probably the hardest to kind of understand. This is the generative adversarial network, but it's again very often used in trying to understand large data sets of images and trying to create and predict off of a data set. So the MNIST database is a series of data that is handwritten notes, handwritten letters. So 0 through 9. The handwritten letters, and what it's trying to do is it's going to try to predict which of those letters, or it's going to be a predictive model that you could use in order to predict those numbers. Sorry. So we're going to set it up very similar. We're going to pre-process the MNIST data set. We're going to set the generator up. We're going to build a discriminator. So in this case, we'll build a generator and we'll build a discriminator. We'll compile the discriminator with an optimizer, a loss function, and metrics. We'll build the GAN by stacking the generator on top of the discriminator, and we'll compile the GAN with an optimizer and a loss function. We'll then train the GAN in a loop where the generator takes fake images and the discriminator learns to distinguish between real and fake images, and the GAN trains the generator to generate more convincing images. Now these new images will then be printed out, and it will also include passing random noise through it, but they'll finally just display out what the final generated images are. So if I can scroll back up real quick to our GAN, that's the process that we're going to go through right here. Okay, so doing the same type of setups here. I'm also going to include a matplotlib because I want to actually see the pictures of the graphics that are produced. I'm going to set up 50 epochs, so that's quite a few. But for this type of a data set, that wouldn't be unheard of. That's not unusual, I would say. We're going to have the batch size be 128, so it's going to take 128 at a time to do a batch. And then we're going to start setting it up. So first of all, we have to pre-process and set up the MNIST database. So I'm loading the MNIST database, and I'm doing a reshape on it so that it'll be something that we can use. I then build a generator, And so very similar to using the different layers as we did on the previous ones. Now this particular generator, I'm going to use the leaky ReLU function as part of it. That's going to come into play at the bottom end when we talk about things that you could have done differently. But in this particular example, I'm going to use leaky ReLU. And I'm also going to include batch normalizations in it. For the discriminator layer, I'm going to use the exact same leaky ReLU, and I'm going to flatten it. I'm going to drop out, and I'm going to use a dense with a sigmoid on it. So the activation sequence in both sets is the same. It's important that you make sure that these are compared and these are matched up, because again, remember, it's going to feed in the generator and the discriminator. If anything is off with these two things, then it's going to not be able to do that final merge together to make the decisions. Here's the compile on the discriminator, and I'm going to use the atom optimizer again. And here is a setting which is going to come into play in a bit, the learning rate. And so I set the learning rate at a default at this point. I'm going to then turn around and build the GAN right here. I'm going to compile the GAN and using the atom and the same learning rate that I talked about. And here again, we're using the binary cross entropy function. And then it starts up a loop. So for each epoch in the range of epochs, so I set it to 50 epochs, it's going to run through this for loop 50 times. Within that, for each batch, it's going to run each batch set. So we set the batch, I believe, at 128, right? Yeah, we set it at 128. And so it'll go through this 128 times the 50 epochs. It's going to generate some random noise to use as the input on the generator, and it's going to generate some fake images to be used in the generator. It's then going to create a batch of the real images from the training data set. It's going to concatenate the real and the fake images together, and then it's going to create labels for the discriminator, fake or real. Next thing it's going to do is it's going to train the discriminator. It's going to generate random noise to input as the GAN. And then it's going to create misleading labels for the generator for those that are fake. And then it's going to train the GAN. And it's going to continue to go through it each time it makes it through an epoch. It's going to list the epoch right here. And it's going to show you the discriminator loss and the generator loss. Now we're going to set this to generate 10 new images based off of the trained model. And then it's going to have some random noise that it puts into it. And it's going to turn around and it's going to kick the generator off to do the predict. And then for each of those images which it generates, it's then going to turn around and do an image show so that you can see what the image looks like. This process here on a pretty decent laptop took a total of a little over 9 hours in order to run. So I will warn you ahead of time. If you want to run this, it's good. It's a good exercise. Just understand that this is going to take a pretty significant amount of time in order to run. Now you can limit down the number of times which it's going to run by changing the number of epochs that you run through. But the fewer epochs that you have, the less trained that the model is going to be. So here is what the final results out of this look like. And the first thing that's going to come out is, that doesn't look like a handwritten number at all. Well, yes, that's correct. So this is kind of the first round of it, and based off of what we're seeing in the loss numbers here, as far as the generator and the discriminator loss, it's like that's why I understand why it's producing like this. And so you can kind of see 10 images here that are coming off. So I included this little section down here too as well. So what figures were used? It tells you a little bit more about the MNIST database. I said about 60,000 labeled images, and you can again see the view of what the 0 to 9 looks by querying the MNIST database. The images don't look like the handwritten. Well, that's true because again, these GANs can be quite challenging to train and require various tuning parameters, so you have to go back and adjust some of those tuning parameters. So some of the ones that I kind of showed you as I was highlighting it as it goes down was increase the training duration, so you could increase the number of epochs that you go through, and you change the batch numbers of the number of batches of images that you get, etc. You could go through that. You could try increasing the number of training epochs, and then see if the increased number is different than the lower number. So if you did this exercise and you repeated it, if you did it with 3 epochs and then you do it with 50 epochs, you're going to see the marked difference in this. The 3 epochs, it really looks just like a mess, just a gray mess that's out there, where after the 50 epochs, it starts to look like an actual digit, a 7, a 9, a 6, etc. So while this still isn't the ideal image, this doesn't really look like much here. There still is the makings of a handwritten 9, the makings of a handwritten 6 is in these images right here. You can adjust the architecture and the hyperparameters. So again, I just listed off a whole bunch of them that we could go through, and we could try doing this, change it, optimize it. But also, if you ran this on GPU accelerated hardware, if we ran this in the cloud environment, we ran this up on AWS or Azure, for instance, we could make it through these iterations much faster, and that would allow you to change the hyperparameters. Spend more time in training, for instance. Once the GAN is trained against that model, then using it from that point forward, you don't have to go back through and retrain it all the time. It's going to be really kind of set. Over time, you may lose fidelity on it, but it's going to have a pretty good predictive rate once you get up in the first part like this. So then it's exploring the various variants. So this is just one kind of GAN. There's a number of different kinds of GANs that are out there. So if you try this particular version and this doesn't work, then try maybe a deep convolutional GAN or a Wasserstein GAN, for instance. Those would be different options that you could have for that. And Keras has, TensorFlow has the option to do that as well. You could increase to have larger and deeper network architectures. So remember, we had those number of layers where you could add more layers and see if more layers would turn around and increase the capacity, increase the accuracy of the model that it produced. That, of course, is going to come at a trade-off of performance as well as the amount of time it takes to generate. And you could regularize the model, so applying regularization techniques such as a dropout or a batch normalization. So you saw in the first examples, we did some normalization of the pixel data, for instance. If you did that, then that could reduce some of the overfitting. It could improve some of the generalization. So that's some things that you could kind of do in addition to try to make that a little bit better. Again, since this takes 9 hours to run this particular example, I wouldn't necessarily recommend you spend a whole lot of time working through this. It's just, again, to give you an exposure of what a GAN looks like. These are not as common as RNNs and CNNs as you've seen in the front, but a student may decide to go ahead and take this on and give this one a shot too as well. So for next week, again, what you're going to do is you're going to create a Jupyter notebook from scratch, and you're going to take one of these 3 techniques and you're going to build a model off of that. If you'd like to use the same data set, that is fine. If you are going to try a different data set, make sure that you load the data set. If you don't have it as part of it, you want to include that with your submission too as well, so that we have it. Or if you have it, like if you download it from the internet, give us the link to where you downloaded it and do one of those download directly into your Jupyter notebook. So then it makes it really easy for anybody to run. So heads up warning again, one final time. The GAN in this example takes 9 hours to run on my computer, so it's probably going to take a little while to run. I would maybe exercise some caution if you decide to play around with that part of it. But otherwise, if you have any questions, please just reach out on the discussion forums in your weekly office hours or directly to the instructor. Thank you.